This is my week 7 video log for my independent study. This week I worked on implementing collision layers so that I could segment colliders into groups to limit which objects detect collisions with which other objects. Here we can show a small demo of it. I've created this create collidable utility method, which just wraps up the functionality of creating an entity, assigning it a transform, setting the transform's position, giving it a mesh, and then setting the radius of the colliders, or setting the radius of the sphere collider. So here we've got, I create one object at the origin and give it collider layer 0, and I create a second object a little bit off to the side, and I give it a I put it on the first layer, and right here you can see that I've enabled collisions between layer 0 and 1, and I've also enabled self-collision for layer 0. And if we run this, and then I hit the tilde key to spit out Gunship's debug output, we'll see that collision is 1 because we've got one collision between the two objects that I've created. Now if I uncomment this line here, now I have a second object on layer 0, and that object overlaps with the first object and it overlaps with the second object, and because layer 0 has self-collision enabled, we should see 3 collisions because there should be a collision between each of the 3 objects. I hit tilde again, and of course we see 3 collisions. And the collision layer system could stand to have more robust testing done with it, not just in terms of performance, but also in terms of correctness, to make sure that I'm correctly detecting collisions in all cases and layers are only colliding if collision is enabled on them. I haven't gotten to that yet. I may not do that here unless I have reason to think that this is incorrect. So this is the interface that I've come up with. When you go to the collidable manager and you create a collidable, you give it the entity like you did before, but now you also just give it the layer, and the layer is just an unsigned int. And when it creates the collider, puts it on the layer. You can then enable collision between 2 layers using the set collision method on the collider manager. You can enable collision between 2 different layers, or you can even enable collision enable a layer to collide with itself. And that's what I've done in this situation. The test that I've written for this is I create 1,000 collidables, 500 on layer 0, 500 on layer 1. Each one has in a random position. And if I give this a run, we'll see that we're getting some 1,200 collisions, and I'm running at 111 frames per second. If we bump this up to, say, 2,000 items, 2,000 cubes, and we do it, we get some 5,000 collisions, and we're at 40 frames per second. So why don't we take a look at how I implemented this. If we go to collider.h, which contains the collider manager class, we'll see now that before I just had an array of sphere colliders, and I treated the collider components much the same as I treated all the other components, where there was one associated with each entity. Now I have a list of this collision layer type, and the collision layer is actually just a collision layer is a struct. Each layer contains a list of the sphere colliders and then a list of their associated entities kept in the same order. That means that meant that I had to update my index map. Instead of just being a map between the entity ID and the index, I now have an index pair, which is a simple struct that contains the row, effectively the layer of the mapped, or of the entity's component, and the column of the entity, or which is the index in that layer. I haven't implemented removing colliders yet, but that's not part of the tested functionality, so I'm not bothering with that for the time being. If we go down into collider.cpp and see how this is implemented, we go to Collider Manager Assign. We'll see that all we do is we retrieve the collision layer for the new collider, and then we push the new collider onto the end of the collision layer. And this is very straightforward. I'm not doing any trickery here. This is very similar to the way that P2 implements the collision layers, where each collision group, as it's called in P2, is just a list of all the colliders in that group, and it's the same thing here in Gunship. Now, what's interesting for Gunship, and I think this is actually pretty similar to how it's done in P2, but I had to think about this for a little while, and I think this is a pretty good method of handling it. When we set collision between two collidables, we first check if it's the same layer, and if it is, then we have a separate list for self-collisions, and that way self-collisions can be handled in an efficient way to avoid duplicates, which is how P2 does it. And then if it's not a self-collision, what we do is up here in collider.h, you'll see that we've got this list of collision, we've got the set of collision pairs. And what collision pairs is it's a list of lists of indices. Each of these inner lists represents a layer. So for example, this collision pair is sub-0, so the first element in this collision pairs represents a list of all the layers that should be collided with layer 0. So all we do is we get the list of layer collisions for the first layer specified, and then we append the second layer to that layer's list of collisions. And what that does is when the collision system needs to go through and collide layers, so if we look at this collide layers method, if we go to collision system update, here where we're performing the pairwise collisions, all we do is we iterate over the outer layer, and then for each of the indices in that list, we collide with it. So we never have to do any checking. We never have to go for each layer, for all of the other layers. If these two should collide, then do the collisions. It's always, there's no branching, there's no branch mispredictions. It's always direct and imperative, which I think is good, and I think that yields pretty good performance. The one implication of this is that we want to make sure that the first layer is always less than the second layer. That allows us to ensure that there's no duplicate layer registration, so we don't register layer 0 to collide with layer 1 and layer 1 to collide with layer 0. It's always the lower layer collides with the higher layer. And right now, just for expediency, I just assert that the first layer is less than or equal to the second layer. The better way to do this would be, if the second layer is lower, just call it with the arguments reversed. And I just didn't do that for the time being, but that's the way I would do it for production code. And then other than that, the collision system is effectively the same as it was before. I mean, now we make a distinction between we have the distinction between colliding two different layers and self-colliding a layer. P2 does the same thing. It just does it. It has separate classes for doing the two of them, but otherwise it's the same. The one interesting thing that I'm doing here for Gunship that's specific to the way that Gunship works, and that has to do with the way that Gunship has to handle collisions with its with the entity component system framework that I've put together, is I've got this right here. I've got collider manager.update cached positions. And if we go to this, why don't we first look at Sphere Collider. Sphere Collider I've added this cached position member to Sphere Collider. This cached position is the location of the transform for the associated collider. When I first implemented the pairwise sphere collision, I iterate for each of the pairs of colliders. I would retrieve the transform for both of those colliders, and then get the position from the transform. That wound up being very slow because it's done as a nested loop. So the first component that I was colliding with, its transform only need to be retrieved once, but the last collider, its transform would have to be re-retrieved for every other item every other collider that collides with it. And that meant I was doing this exact same get action possibly hundreds or thousands of times for each component. And that wound up being very expensive to repeat that same work. So the way I'm getting around that is to cache off the position. If we go to collider.cpp, I've added this utility method into the collider manager to update the cache positions. And what it does is it just, for each collision layer, and then for each collider in that layer, we get the transform for it, and then we cache off its position. And that guarantees that we only need to retrieve the transform for a collider exactly once each frame. Now, this seems potentially like it could be a downside of the entity component system's overall design, since I don't just have a pointer to the position. I have to do extra work. I have to do this extra work to effectively work around the framework that I've designed. However, I would argue that that's not the case. This style of caching off repeated work is applicable just about anywhere. For example, in P2, there is I don't have it open, but in the collision method, there's a bunch of repeated work in P2, and actually I did some optimization work in P2 this week in the collision system, and I did effectively the same thing. It was doing work calculating the world transformation matrix to get the position of the object, and I changed it to just directly store the position and set the position once and just cache off the value that it actually needs to use, rather than recalculating it a bunch of times for every collision pair. So while this is just a different type of information that's getting recalculated, like specifically retrieving the position isn't something you have to do in P2, but it is something you have to do in Gunship. The fact that there's work that's repeated that needs to be cached off, that's not something that's specific to this framework design. I don't think that's a pitfall of this of the framework that I've put together for Gunship. Why don't I also quickly show off P2. I've set up the same collision test in P2, and I've made a sample collision object, and I've templated it so that I could effectively have the same layer system. And I do the same setup as I do in Gunship, where the collider cube 0 is set to collide with itself, and then collider cube 0 is set to collider cube 1. Now I've got 500 of them, and when there are 500 of them and we run it, we'll see that we're getting some 90 FPS. That's a 10 milliseconds update time. And if we were to bump that up to 2000, then we'll see we're getting some 20 FPS. I've started doing profiling and optimization work in both P2 and Gunship. And I got through some major bottlenecks, but at this point, and so now at this point I've got smaller things to work on. I've got to find maybe more hidden bottlenecks, the ones that aren't less obvious. I'm actually not sure how much more improvements I'll be able to get done. At this point, it seems like if I were really working on a game engine, if I weren't like focusing on getting stuff done for finals, the next thing to do would be to start working on broad phase collision detection, like implementing collision groups and doing like bounding sphere collisions and AABBs for groups and stuff like that. Because really what's gonna speed up the collision detection for both of these engines is simply doing fewer collisions. There's not much I can do with the existing collision systems to make the just tons and tons of pairwise collisions that are being done to make that any faster. However, I do want to show off Intel VTune, which is the new profiler that I've been using. I was having some trouble with it previously. I finally got it working again on my system. This is the latest profiling information from Gunship. This is the summary tab, and it looks pretty much like what you would expect. It's just got a list of the top hotspots. It's got some basic information about the profile that was being done. It looks like Intel's profiling tools are very heavily focused on multi-threading. So one of the things it has right here at the forefront is information about your CPU usage. I'm not doing anything with multi-threading this quarter. However, I think that would be something interesting to work on next quarter if I wanted to continue with the collision system. Definitely one of the ways that I could improve just this collision system right now is through concurrency. With the collision layers and without any collision groups, it would be very easy to parallelize it because there's no worry about overriding data. So why don't we take a look at what I was talking about with it's simply there's just a lot of collisions happening. This sphere collision method, if we take a look at it, this is the method where the collisions themselves actually take place. And if we look at this top-down tree method, we'll see that it's being called from two different locations. It's calling from self-collide layer and collide layers, which makes sense. It's the only two places that are calling it. And we'll see that in terms of bottlenecks for the code, I mean that's it. Like the only place that's slow at all are the sphere collisions. It's simply a lot of collisions are happening, and I can actually shrink this down. In terms of bottlenecks, like nothing else is taking up time. It's just the sphere collisions. And if we look at the source, VTune's got this nice setup where you can look at the source code and you can see which lines are actually taking a lot of time. And in calculating the collision, the things that take time are calculating the squared distance, because I'm not even doing a square root. I'm just doing it with the squared distance, and then actually doing the comparison and returning it. And I don't know. There's not much else I could do to speed this up. I could perhaps enable fast floating point operations, and I don't know that would even speed up something like this. I think enabling fast floating point operations only really helps with stuff like square roots or anything in like the C standard library. But this is like this is only showing up on the bottleneck simply because it's being called so many times. If we look higher up here for, say, the self collide layers, and we view source, and we can look at if iteration is taking a lot of time, because that was a bottleneck in P2 previously, because it was using STL containers. Iterating over STL containers was slow, so I had to swap to some faster stuff. I actually copied over the fast array class that I had implemented in Gunship over to P2 to be able to speed up iteration times. And you can see here that, iterating over this outer list takes no time, and iterating over the inner list takes almost no time. Is the actual collision comparison that's taking a lot of time. So what this is telling me is that there's really not much I can do in the way of optimizations. It's going to come down to algorithmic improvements, which means collision groups just doing something to make sure that I can perform fewer collisions. At least that's the case for Gunship. If we look at P2's collision or performance profile, it's pretty similar. If we take a look at this test collision pair method, that's the same as that sphere collider pair that I was just showing. Then we'll look at the top-down tree. We'll see that test collision pair is called by the collide two different layers method or class, and the other one is somewhere in here. There's the self collision test method, but here we go. Collision single processor. Here we go. And so those two show up as the dominant items on the list. And in P2, the story isn't quite as straightforward. So it's got a lot of stuff like this, where it's got like constructors and destructors and a bunch of little fiddly stuff that's taking up small chunks of the time. So I could potentially there's a lot of vect constructors and vect operators that are being called that are leading to a bunch of overhead. So I can still optimize P2 a bit. Like you might have noticed that P2 was quite a bit slower than Gunship. I might still be able to get it up to speed, but P2 is largely in the same category or in the same spot that Gunship is right now, where it's slow because there are a lot of collisions being done, and there's no way to reduce it without doing more advanced collision detection stuff that I'm just not going to be doing until next quarter if I choose to continue with collisions. That's my report for so far. What I've got coming up ahead of me is more performance and optimizations. I'm going to see if I can finish up with those last big bottlenecks in P2, and then if the performance is still different between P2 and Gunship, I'm going to want to really dig into why that is the case, and see if I can figure out, if I can pinpoint where it's coming from, and see if there's anything specific in Gunship's design that makes it faster, or vice versa, if that's what the case is. And then it'll be on to finishing up, getting together a final report on Gunship, and perhaps spending some time cleaning up Gunship, finishing up any things that I haven't done. Like I've just been kind of skipping over minor pieces of functionality for the collision system just because I'm not actually using them at the time. I'm not making a game with Gunship, so there's just stuff like being able to disable colliders is not something I'm worried about right now, but I might add that if I have time. But that's it for now. I will see you again next week.